Let's talk about something that feels a bit like magic. How does a computer, a machine that only gets logic and numbers, actually understand something as messy and beautiful and human as language? Well, the answer is way more like a map than it is like a dictionary. Let's dive in.
So it all boils down to this one simple question. A computer only understands numbers, right? Just ones and zeros. So how in the world does it know that the word apple and the word banana are related? It's not magic, I promise. It's all about location. And here's the secret, right here. The computer doesn't even try to understand what an apple is. Nope. Instead, it gives every single word a coordinate. Think of it like a unique pin on a giant sprawling map of meaning. This simple idea, a GPS for words, is the key to unlocking this whole thing.
So yeah, let's call this concept a GPS for words. It's the fundamental idea that makes all of modern AI language work, and it really starts with one key technical term.
Okay, so that technical term is embedding. It sounds a little intimidating, but it's really just a fancy word for a super simple action, taking a word and planting a pin for it on this giant map. Every single word you can think of gets its own unique spot.
The rules for this map are actually pretty straightforward. First, like we said, every word gets a coordinate. Second, and this is the entire secret to everything, words that have similar meanings are placed close together. So apple ends up being a neighbor to banana, but it's going to be miles and miles away from car. That's it. That is the whole trick.
Okay, so how does the computer actually build this map in the first place? Well, it happens in this kind of four-step journey that takes any sentence you can imagine and turns it into pure, simple numbers.
Here's the whole assembly line. First step, tokenization. You just break a sentence into its individual words. Easy enough. Step 2, assign IDs. Every unique word gets its own special number, like a serial number. Step 3, this is where it gets cool. Those numbers are turned into big lists of other numbers. We call them vectors, and those are GPS coordinates. And finally, step 4, the computer just starts to learn. It reads billions of sentences to figure out where each and every coordinate should go on its map.
And this is what you end up with. To the computer, the word apple is totally gone. It's been replaced by its vector, its coordinate. It's now just a list of numbers that represents its location in this giant space of meaning.
Now for the really clever part. How does the machine know where to place all these words? It doesn't have a dictionary to look things up. It builds its own map by just observing one very simple rule about how we humans use language.
This one sentence right here is the foundation for everything. It's the only rule the computer needs. Words used in similar situations mean similar things. So if two words keep popping up interchangeably in millions of sentences, the machine just assumes they've got to be related.
Let's look at a real example. The model reads millions and millions of sentences. It sees I like apple, I like banana, and I like mango over and over and over. It has no idea what like is or what an apple is, but it sees a pattern. It sees that these three words can all kind of slot into that same spot. So it concludes, hey, these must be related, and it nudges their GPS coordinates just a little bit closer together on the map.
And it's the same exact logic for everything. The model sees dog is running and cat is running. Again, doesn't know what a dog or a cat is, but it knows they appear in the same context, so it nudges their pins a little closer together. Now just imagine this process happening billions of times for practically every word on the entire internet.
So after all that learning, what do we actually end up with? We get this incredible, fully fledged map of meaning, where the distance between any two words tells us something about their relationship.
And the final map, it really does look like a real one. You get these little clusters, these neighborhoods of meaning. You'll find all the fruits hanging out in one area, all the animals are in another part of town, and completely unrelated concepts like car, yeah, that's way over on the other side of the map. It is literally a geography of our language.
So look, if you remember just one thing from all this, make it this. The entire goal of embedding is to create a system that turns words into numbers in such a way that similar words get similar numbers. That's it. That's the whole game.
And this is the fundamental insight that changes everything. When we see the word apple, we think of the fruit, its taste, its color, the whole experience. The machine sees none of that. It only sees a coordinate, a vector. It's not performing understanding, it's performing math. It's just comparing a location of this vector to the location of all the others.
And that leaves us with a really fascinating final question, doesn't it? If a machine can navigate this map of meaning so perfectly that it can talk, write, and even reason with us, is that the same as understanding? Or is it just an incredibly sophisticated, brilliant master of mathematical geography? Something to think about.